Hello and welcome to today's video. Sorry about this kind of late upload, but we're finally on to topic 3.1, derivatives and polynomials. So first, I wanted to start by asking, or even proving, that what the derivative of d, or what is the derivative of a constant c? Well, the answer to that question is always 0, and let me show you why. We know the definition of a derivative. So the d over dx of c here is really the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. So d over dx of c, well, we have a function c here, and c is just a constant. It has no x's, so we can't put this x plus h. So we get c minus c over h. Well, with that in mind, whenever we take the limit as h approaches 0 of 0 over h, this h isn't going to actually be equal to 0. It's just going to be 0. So this is really just going to be equal to 0. So continuing on, or to summarize what this really means, is the derivative of any constant c is equal to 0. So if I asked you what is the derivative of pi, that is equal to 0. If I asked you what the derivative of e is, that is equal to 0. If I asked you what the derivative of 10 to the power of 300, guess what? That is also 0. Okay, so now that we know the derivative of constant, what is a derivative of a line? What is the derivative of x? Well, the derivative of x, once again, we start out with the limit definition, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, in this case, what we're going to be plugging into, our f of x is x, so we get x plus h minus f of x, which is x, all over h. Our x's cancel, our h's cancel, and that just leaves us with 1. The limit as h approaches 0 is just 1. All right. So the derivative of a line is just 1. All right. Now it is time for a wonderful proof. So recall, and I want us to remember just for a moment, that what is going to be a derivative of a basic polynomial x to the n? What is the derivative of x to the power of n? Well, once again, we start out with what we know. We know the definition of a limit is the limit as h, or the definition of a derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, we are going to take this x plus n, since this is our function, so our function of x is x to the n. So if we say that f of x plus h, that's just going to be x plus h to the power of n minus f of x, which is just x to the n, all over h. Well, what can we do with this? You may recall from your pre-calculus days a wonderful theorem. This theorem's name is the binomial theorem. So, we are going to use said binomial theorem to expand this out. So, we know that we have an n power here. So, our derivative of, or sorry, if we want to expand this out, we are going to get x to the power of n plus n to the power of x to the n minus 1 times by h plus n, sorry, n, what's it called, times by n minus 1 divided by 2 times by x to the power of n minus 2 times by h to the second. Okay, adding on to that, so I'm going to dot, 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 just to show that this is going to go on for a while. If you know the full binomial theorem, you'll know where it goes. But at the very end, there's going to be a h to the power of n. And all of this is over h. Well, and then we also have a minus x to the power of n. Well, this x to the power of n and this x to the power n are going to cancel. And all of the terms of the binomial theorem are going to have h's in them. So we are going to be left with the limit as h approaches 0, and this h and that h are going to cancel along with that, and just so on. It's going to continue canceling. So we are left with the limit as h approaches 0 of n times by x to the power of n minus 1 times by, and we don't have to worry about that k, plus n times by n minus 1 all over 2. Apparently I miswrote it up there, but it's over 2. Times by x to the n minus 2 times by h dot, 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 plus h to the power of n. Well, the cool thing about this is, because all of these terms other than this one have an h, everything else here is just going to go to 0 as this limit approaches 0. So really, this d over dx of x to the power of n, geez, my pencil is having a not so nice time. Gonna have to reset it later. Alright. And we are just left with this n to the x to the n minus 1 is our derivative of any x to the power of n. And this here is called the power rule. Alright. So now let's go on to our next rule that we have, which is the constant multiple rule. So assume, alright. So let's see. I want to see how I want to do this. The constant multiple rule. If c is a constant, and f is a differentiable function, then the derivative of c times by f of x is equal to c times by f prime of x. Alright. Or in other words, just so I can better express this property, d over dx of f of x. So we're going to use a small bit of a limit rule here. So we want to let h of x be equal to c times by f of x. Alright. So if we want to take the derivative of this, so let's take the derivative of this function. So if I want to know what h prime of x is, we are going to take the limit as h approaches 0, and I realize now that this was a kind of bad choice for like h, of h of x plus h minus h of x h of x all over h. Well, we know that this h of x is going to be equal to c times by f of x plus h minus c times by f of x all over h. And we're still taking the limit as h approaches 0. Okay. H prime of x, then, in this case, is going to be the limit as h approaches 0, and I'm going to just factor out that c times by f of x plus h minus f of x all over h. Well, then h prime of x, because we can pull out that c, is equal to c times by the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, what is this? This is just the derivative. This here is just f prime of x. So we get c times by f prime of x is equal to h prime of x. So we can clearly see that this property holds up. And as thus, we have proved the constant multiple rule. All right. And now I just have one more set of rules really for us to go over. And I can once again prove them for you. So, the two following rules, and I might actually have to move these a bit further down. But that's all right. So, we are going to say the sum and difference rules. D over dx of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. All right. And similarly, the derivative of f of x minus the g of x is equal to the derivative of f of x minus the derivative of g of x. All right. So I think the easiest way for you to show you that this is true is by adding up these derivatives. So I want to define a new function, and we are going to call this function q. So let's call this function q of x is equal to is equal to f of x plus g of x. All right. Now let's say I want to find the derivative of q of x. So once again, we always start out with our limit definition. So we have a limit as as h approaches 0 of q of x plus h minus q of x all over h. Well, we can expand this out, so we get q prime of x, really, this is what that needs to be called. Q prime of x is equal to the limit as h approaches 0 of f of x plus h plus g of x plus h. And I'm just getting this from plugging in the fact that this q of x or q plus h is going to be plugged into both of those, minus f of x minus g of x all over h. Well, I'm kind of running a small bit low on space here, but what I'm going to do now is I'm going to do a small bit of rearranging. So we're going to go back up over here just so you can continue following the process. So we're going to now group these f of x and the g's of x together. So we're going to say f of x plus h minus f of x plus g of x plus h minus g of x. Want to move that. All right. And we're taking the limit as h approaches 0. I'm going to erase that. Of all of that over h. Well, we can now further break this down into the f of the left and the right portion. So we're now going to call this the limit as h approaches 0 of f of x plus h minus f of x all over h minus, plus, and I'm going to put this all in parentheses, g of x plus h minus f of x all over h. And I'm going to close that for right now. Okay. Now what can we do? We can use our properties of limits and say that the limit as h approaches 0 of f of x plus h minus f of x all over h is equal to plus the limit as h approaches 0 of g of x plus h minus f of x, or apparently at some point there it is, g of x minus g of x all over h. And that's true. We can break down a limit as such using our limit properties. And now for the final show, q prime of x is equal to, this up here is just f prime of x. That's the definition of f prime. And over here is the definition of g prime. So we can see that whenever we take a derivative of two functions being added together, it's just the sum of the derivatives. And the reason why this works for a negative function is because in theory you can just slap a constant as a negative. I won't go into too much detail onto how to do that, but it exists and this is just the proof of it. Alright. So now that we have all of these rules, let's use them. So starting out we have I, which is going to be x squared plus 3x plus 2. Well, let's find the derivative of the following functions. The first one, well, the derivative of this is the product of the derivatives. So this is really saying the derivative of x squared plus the derivative of 3x plus the derivative of 2. Well, this first one's easy. This is a power rule. So this is, I should have really explained this earlier, but we have a function to an n power. In this case, we were using x squared, and it's going to be equal to 2 times by 2 minus 1. So in this case, it's going to be 2x. Alright, so here we have a derivative of a line, but we're going to use our constant multiple rule to pull this out front, so we get 3 dx of x, so we get plus 3. A derivative of a constant is 0. The next one, we have x to the 5th plus x to the 3rd plus 4. Alright, once again, we break this down. We say that we're taking d over dx, And this d over dx actually does distribute, which I find interesting. So we get d over dx of x to the fifth plus d over dx of x cubed plus d over dx of 4. Well, we pulled out this out front, so we are going to get a 5. 5 minus 1 is 4. For the next one, we get 3 times by x. 3 minus 1 is 2. The derivative of a constant is just 0. Alright, for this last one, this one's a small bit more powerful, or a small bit more challenging, and what I'm going to say is do the algebra first. So, this first part can't be simplified anymore, but doesn't need to be. But how do we take a derivative if it's like in the denominator? Well, we don't have a rule for that just yet, but what we do have is we know that 1 over x is the same thing as x to the power of negative 1, so this is just x to the negative 1 power. Now we can take the derivative of this. So we have 2/3 of x to the negative 1/3 power, since 2/3 minus 1 is negative 1/3. The power rule works for any x raised to a power. However, this is a very strong note. D over dx of a function, let's say 3 to the x, does not equal x times by 3x minus 1. This does not equal that. That is a power function, or an exponential function. Rather, I misspoke originally. But it does not have the same derivative rules as a power. Alright. For this next one, we want to say minus 1 times by x, and negative 1 minus 1 is negative 2. So our final answer is 2/3 of x to the negative 1/3 minus x to the negative 2. Alright, continuing on, we have exponential functions. So, I'm going to kind of show you what a derivative of an exponential function is, and then I'm going to tell you it. So, because it's kind of hard to really approximate, so we're going to say that we have f of x is equal to b to the power of x. So what we're going to do to find f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, f prime of x then is going to be equal to the limit as h approaches 0 of b to the power of x plus h minus b to the x all over h. Well, what can we do with that? Well, f prime of x then is equal to the limit as h approaches 0. Well, let's see. What can we do? We can use our exponent rules to realize that we can break this out. We can factor out a b to the power of x to get b to the power of h minus b to the power of 0. And I'm going to leave it like that for a reason. And all of this is over h. Okay. Now what do we do? Well, f prime of x is equal to the limit, is equal to b to the power of x times by the limit, as we can bring this b to the power of x outside because it doesn't have an h in it, of h approaches 0 of b to the h minus b to the 0 all over h. Well, You may recognize that this may not be our normal form of, like, the h approaches 0 of f of x plus h minus f of x, but this actually does resemble a function. Surprisingly enough, this resembles the other definition of a derivative. So really, this is f prime of x times by b to the power of x times by the derivative of f prime of x evaluated at 0. If you really want to, you can just swap out this a's to make it, or these h's for a's to make it a bit clearer. But you can see that this is really just the derivative at 0. Alright. Well, this tells us a lot of useful information, but what is this number? We can't really solve for it, but we can use the limit to somewhat try and estimate it. Well, I'll actually tell you what that number is, and once we know the chain rule, I'll prove it for you. So the derivative of the derivative of b to the power of x is equal to the natural logarithm of b times by b to the power of x. So the derivative of e to the x is actually a lot easier to do than this, because if I want the derivative of e to the x, and e to the x is an exponential, well, what you'll see is that we get the natural logarithm of the base, which is e, times by e to the x. Well, what does that evaluate to? Surprisingly enough, e to the x. The derivative of e to the x is such a cool function, and we want to work in e to the x whenever we're doing calculus. I'm actually going to erase this entire portion up here, as I feel like this video is running a bit long, and I don't want you to bore you with that extra bit of practice, but I do have some following functions I'd like us to find the derivatives of. So, let's see. We want find the derivative of the following functions. So, g of x is equal to 6x plus 7. So what we're going to do is we're going to apply the derivative operator. We get g prime of x. We get a constant times by the derivative of x plus the derivative of 7. Alright, well, g prime of x then in this case is going to just be 6. Alright, let's erase our work and continue going. We now have h of x. H of x is equal to negative 2e to the power of t. Well, apply the derivative operator. Or sorry, h of t this should be. Oop. Sorry about that. H of t. There we go. And apply the derivative operator on that side. Okay. And I want to fix that t as well. So, what we're going to get, we get h prime of t is equal to negative 2 times by the derivative with respect to t of e to the power of t. Well, we know that the derivative with respect to t of e to the power of t is just going to be e to the t. So we just get negative 2e to the t. That's easy. Okay. So we get is equal to negative 2e to the t. Okay, let's erase our work and do another. Let's see. Y. So we're going to use our y prime notation. So y is equal to t cubed plus t pi plus e to the power of t plus pi to the power of e. Alright, let's start this. So take the derivative with respect to t. So we get y prime is the derivative with respect to t of t cubed plus the derivative with respect to t of t to the power of pi plus the derivative with respect to t of e to the power of t and plus the derivative with respect to t of pi to the power of e. Well, in this case, y prime then, the derivative of t cubed is 3t squared. Alright, plus the derivative of t to the power of pi. Well, the derivative of that's going to be pi times by t to the power of pi minus 1. What is the derivative of e to the power of t with respect to t? That's just e to the t. Alright, and then finally, the derivative of pi to the power of e, that's just a constant, so 0. Alright, so we found this, y prime is equal to this kebab. And now I can delete, now I can delete the rest of this. Alright. R prime of t is equal to, well, let's actually first start by rewriting the algebra. So r of t is a times by t to the negative 1 plus b times by t to the negative 2. Alright, because b over t squared is just b, is b times by t squared. Alright, to the negative 2, sorry. To the negative square root. No, that's not real notation. Alright. Well, if we want to find r prime of t then, that's just going to be negative a to the t to the power of negative 2. Oh, wait, I should probably show my steps. I apologize. Negative a times by d over dt of t to the power of negative 1 plus b times by the derivative of t to the negative 2. Alright, so then we can now apply our rules. This first one, we're going to get a negative a t to the negative 2 plus or minus a negative 2b to the t to the negative 3. Alright. Well, I've got 2 more examples for you, and this is kind of strange, and I should be able to delete down here because apparently I wrote the same question twice. Tired me. Alright. So I want you to find dx and dy, dy dx and dy dt of the following functions. So, even though this has 2 variables technically, whenever differentiating this, I want you to treat the variable that you're not differentiating with respect to as a constant. So, in this case, whenever I go to find dy dx, so we're going to say y is equal to tx squared plus t cubed x. Well, we're going to take the derivative of both sides with respect to x. So we're going to get y prime is equal to t times by the derivative of x squared plus t cubed times by the derivative with respect to x of x. Well, solving now, we get t is equal times by 2x, which I'm just going to real quickly bring that 2 out front, plus t cubed, and that's our answer. Now we're differentiating with respect to t. Y is equal to tx squared plus t cubed x take the derivative with respect to t. Alright, well, now our x squareds are constant. So y prime is equal to x squared times by the derivative of t with respect to t plus x times by the derivative with respect to t of t cubed. Alright, so then our y prime, the derivative of t with respect to t, that's 1. Times that by x squared, that's just x squared. Alright, the derivative with respect to t of t cubed, that's 3t squared, because we pull the 3 out front and subtract 1 from the exponent. So what we get is we will get 3x t squared. And those are answers. The next question we have is, when does the graph e to the power of x minus 2x have a horizontal tangent? Okay, so this question is actually a small bit difficult. So, the first things first that we need to do is ask, what is a horizontal tangent? That is whenever a horizontal tangent is when the slope, the tangent line has a slope of 0. I don't know why I'm writing that out, but it's whenever the tangent line has a slope of 0. Well, we want to then, I suppose, find whenever the derivative is equal to 0. So let's start out by finding the derivative. So f prime of x is equal to e to the x minus 2x. Or sorry, f of x. Now I'm going to take the derivative with respect to x. So I get f prime of x is equal to the derivative of e to the x minus 2 times by the derivative of x. Alright. Well, if that's the case, then f prime of x is equal to e to the x minus 2. As the derivative of x is just 1, and the derivative of e to the x is e to the x. Well, now let's solve that for 0. So 0 is equal to e to the x minus 2. Well, move the 2 over to the other side, so I get e to the x is equal to 2. Well, how do I get an x into the base? Or out of the exponent, we take the logarithm. So the natural log of 2 is equal to the natural log of e to the x. The natural log of e to the x will cancel, leaving an x is equal to the natural log of 2. So it will have a horizontal tangent at x is equal to 2. And now I want us to find the normal line to the curve square root of x that is parallel to 2x plus y is equal to 1. Okay, this is a doozy. So to start out, let's get this 2x minus by itself. So we are going to get y is equal to negative 2x plus 1. And we want a normal line that's parallel to this. So our y normal needs to have our slope normal, it needs to be negative 2. Well, how do we know what a tangent line? What even is a normal line? A normal line is the line that's perpendicular to the tangent line. So it's perpendicular to tangent line. So the formula for finding the reciprocal line, I believe that's what that's called, but is just going to be, normally it's 1 over, slope of normal is really just 1 over, negative 1 over slope of tangent. So if we have this, we can say that negative 2 Yeah, negative 2 is equal to negative 1 over mt. Well, let's solve this for mt, so we get negative 2 mt is equal to negative 1. So mt is equal to 1/2. Alright, what do we do with that? Well, now we need to find the point on the curve that is... now we need to find the tangent line that has a slope of 1/2. So we are going to take, or we have y is equal to the square root of x. You may recall that this can be rewritten as y is equal to x to the 1/2. This then we can now take the derivative of with respect to x. So we get y prime is equal to 1/2 x to the negative 1/2, because we bring this out front, subtract 1. Alright, and now what? Well, we just need to solve this for 1/2. So we get 1/2 x to the negative 1/2. Surprisingly enough, this and this cancel. So we just want to know whenever... I'm almost out of space, so I'm going to just continue this down here. So 1 over 1/2 is equal to 1 over 1/2 x to the negative 1/2. Alright, well, this and that cancel, so we are just left with 1 is equal to x to the negative 1/2. Well, this is really just the same thing as 1 over the square root of x is equal to 1. Let's multiply both sides by square root of x is equal to 1. Square both sides, and we get x is equal to 1. Honestly, I could have shown that in a few fewer steps, but I wanted you to really get a walkthrough of the entire process. Well, that's all I have for you today. I hope you enjoyed and found this video informative, and I hope you all will like and subscribe so you can hear more content from me. Alright, goodbye. Have a great rest of your day.